Yeah, I'm Shuai Yan. I'm now a postdoc at University of Washington, working with Michelle Gundick and TJ Fudge. Before I moved to Washington, I got my PhD at University of Texas at Austin, working with Don Blankenship and Duncan Young. Um, so the talk today will focus on the basal ice unit, the very bottom part of the ice sheet in East Antarctica. And I'll mostly use the NSF Codex dataset. So I figure I should start the presentation with a brief introduction to Codex. So NSF Codex is a science and technology center founded with a mission to explore Antarctica to find the oldest possible polar ice sample and then leverage that sample to understand the evolution and the future of our climate system. It's a huge team. There are, I think, more than 15 different institutes involved in this. I don't know whether I have the most accurate number on that. And essentially the goal is to find two separate sets of ice cores. So the first set would be a continuous ice core that could provide a continuous and intact climate record for the past 1.5 million years. And then beyond that, we're hoping to find discontinuous but really old ice cores that could provide some snapshots of very old climate record. So yeah, for the discontinuous core, we have been exploring the blue ice area near Island Hills and Elephant Marine. And for the continuous core, which is what I'll focus on today, the Codex team has been doing surveys in the southern flank of Dome A, basically between Dome A and South Pole Station. Now, the exploration of the interior is essentially done by two steps. The first step would be airborne survey, which can cover a big area of interest fairly efficiently. And then after that, the ground geophysics team will go out to do a more targeted survey in a relatively smaller area. In the past 2 seasons, the airborne team has been working really hard in the southern flank of Dome A. The platform we used actually have 2 different separate radar systems on board, and we also have barometer and magnetometers and laser altimeter and other instruments on board as well. So for the past 2 seasons, we have done 31 survey flights based from South Pole, flying toward Dome A. And in total, we have collected more than 58,000 kilometers of data. And here's a map of the airborne geophysics transect. So the ice flow in this region starts from Dome A, which is on the top right corner of this map here, and it flows generally towards South Pole and takes a slight turn to the west after it hits South Pole. So you can see the majority of the transects, actually, they are collected parallel to the ice flow direction, which is actually very helpful for modeling purposes. And some of them are flown orthogonal to the ice flow direction, mostly to connect those survey lines and provide tide corrections for potential field data. Here's a typical radargram from such a survey from the UTIG radar system. I should say, for my project, I mostly use the UTIG radar product. Essentially, it's a cross-section of the ice sheet. You can see the surface, you can see the bedrock, and those beautiful internal stratigraphies within the ice sheet. And obviously, we can measure the thickness of the ice sheet, the basal topography, and they're all very important boundary conditions for the ice sheet dynamics. And by studying the internal stratigraphy, we can essentially understand the past evolution of the ice sheet dynamics. And now we're developing capacity to look into the internal fabric structure as well. And from, we can extract the amplitude of the echo power for each reflective horizon and then estimate for the internal attenuation rate, which is essentially a function of internal temperature. And as well, radar is also a very powerful tool when it comes to identifying subglacial water, subglacial lakes. So by mapping out the location of subglacial lakes, we can provide some certain constraints to the geosmoke flux estimation. We can study how the presence of subglacial water impact the overall dynamics of the ice sheet. So I just want to show a few examples of data products we have so far. So here is a much improved mapping of the subglacial topography from this new Codex dataset. Here's the Gambursiv Mountain, really, really rough topography. And we have a huge basin right between South Pole Point and Gambursiv Mountain. For now, we're just calling it the South Pole Basin. There's a small mountain inside the South Pole Basin, the Elbow Mountain, and the recovery subglacial highland here, and a very deep trough right next to the recovery highland. And yes, and then when we calculated the subglacial roughness from the bed topography, which is essentially how many meters of variation happens over the distance of, for this case, 400 meters of horizontal distance. We noticed that the South Pole Basin is essentially divided into two parts. The inner South Pole Basin is quite smooth. The roughness is close to zero. The outer South Pole Basin is much rougher than the inner. And then we looked into the distribution of subglacial lakes. Very interestingly, almost all of the subglacial lakes we can identify from radar sounding, they are all in the inner South Pole Basin where the bedrock is quite smooth. So they all work in prep for this subglacial hydrology work, especially is led by a Codex PhD student, Megan Kerr, who is actually in the field right now. I'll talk about it later. So yeah. Oh, by the way, I should say all the radargrams from Codex is now available to the public. We uploaded all the radargrams to Texas Data Repository. So if you go on TDR, everybody could download the radargrams and the later altimetry data as well. And we have another PhD student at UT Austin working on the internal stratigraphy of the ice sheet, trying to understand the past evolution of this part of the East Antarctic ice sheet. Me, myself, for the past year or so, I have been working on the part of the ice sheet where we don't see any stratigraphy, the very bottom portion of the ice sheet, the basal ice unit. Now, the idea of basal ice unit, the topic is not new at all. There has been so many different studies done on this topic in Antarctica and in Greenland as well. Just to name a few, right? There's no way I can name all the previous studies. It wouldn't be possible. But just to name a few, there has been several studies looking into different sites in East Antarctica, trying to understand why we have the basal ice unit and what is controlling it, how does it form, and how does it evolve throughout time. One thing I noticed when I did my literature research is that the terminology has not been consistent. Essentially, people has been using different names and terms to describe the same stuff in some cases. So I figure I should clarify my terminology before I dive into it. So you will hear me using the term basal ice unit. By that, I mean the part of the ice sheet where we just don't see any stratigraphic horizons. The top 3/4 of the ice sheet, normally we see those beautiful internal horizons. They're essentially a record of past ice dynamics. But the bottom portion of the ice sheet, sometimes we just don't see those horizons. That's the definition for the name basal ice unit for my talk only. Now, it doesn't mean we don't have any return power at all for this part. So in some areas, our radar sounder can pick up some energy for this part, but those return energy, they are not in the form of a stratigraphic horizon. You can't trace layers in them. So I'll refer to them as diffuse echo, those fuzzy looking cloud of return power. And in some areas, we just don't have any echo power at all. I'll call them echo free zone, which is actually a term that has been around for quite a while. So yes, and yeah, with the new codex dataset, we have been able to map out the thickness variation of the basal ice unit. Again, where we don't see those beautiful stratigraphy. And here's the result we have. So yeah, bright yellowish color means very thick basal ice unit, and dark bluish color means very thinned out basal ice unit. Now we do see some very interesting trend. Near Gambersiv Mountain, the basal ice unit tends to be thinner, and once as the ice flows towards South Pole, it gets thicker and thicker. But then the thickness of the basal ice unit drops quite sharply here. The unit thickness decrease for multiple hundred meters of the distance of 10 kilometers or so. A very sharp decrease. And yeah, we traced out this sharp transition boundary. We don't really have a name for it yet. So for now, I just call it the mid-South Pole Basin boundary. It's definitely one of the most interesting features we see on this map. Another feature I want to point out is this part is essentially a thin patch in the middle of a relatively thicker basal ice unit. Again, we don't really have an official name for it yet. For now, we're just calling it the platter site, which the platter site is actually one of the target sites for our ground team this season. Yes, so here's a map of the fractional thickness of the basal ice unit, basically how much of the ice sheet is the basal ice unit. You can see near Dome A, above the Gambersiv, the percentage is about 15%, and then it increased to around 20-25%. The platter is still around 15%, and then this 20-something percentage fraction decreased quite sharply into about 15, 10, or even lower than 10% in some areas. So yeah, we still see this transition in the fractional thickness map as well. Now, when we plot the mid-South Pole Basin boundary on the topography map, we notice there's barely any correlation between the boundary and any topographic feature. The boundary is kind of touching the elbow mountain, but that's it. For the rest of the boundary, it's just sitting in the middle of the South Pole Basin. So basal topography does not appear to control the basal ice unit thickness, or at least it's not the most important players in the field. So that's about the basal ice unit. Then we moved on, we traced out the presence and the thickness of the diffuse echo, trying to distinguish diffuse echo from echo-free zones. And then we calculated the fractional thickness of the diffuse echo itself. So basically this map shows how much of the basal ice unit is filled up with such diffuse echo. So near Gambersiv, the percentage is over 58%. Is the majority of the basal ice unit is filled up with diffuse echo. But as the ice flows downstream, we see this percentage start to drop. Essentially, it disappears when the ice enter the South Pole Basin. Interestingly, though, when the ice hits the recovery subglacial headland again, the diffuse echoes start to show up again. So you see here, it started with about 40-50% and then decreased to about 20%, disappear, and then shows up again once the ice hit the recovery subglacial highland. So we wonder what is causing this diffuse echo, what is controlling the thickness variation of the basal ice unit, which obviously has great implication for codex, because if you want a continuous intact ice core, by definition, the most bottom part of the ice core holds the oldest climate record, right? So understanding the dynamics and rheology of the basal ice unit comes with huge implication for old ice exploration. So we plot out the boundary and we compare the presence of diffuse echo on the map of subglacial roughness. We notice a very strong correlation. So this mid-South Pole Basin boundary basically is the boundary of basal roughness. When basal roughness is kind of high, we see a thicker basal ice unit. And when the bed turns to super smooth in the inner South Pole Basin, we see a sharp decrease in the basal ice unit thickness. And we see another very strong correlation between the diffuse echo presence and the basal roughness as well. So near comprehensive, where basal roughness is super high, we see a very strong signal of a very strong presence of diffuse echo. When the basal roughness start to decrease, diffuse echoes start to fade away. And when the basal roughness increase again near the recovery subglacial highland, we see the diffuse echo show up again. So there's this strong correlation, but correlation does not always mean causation, right? There could be something else controlling both of them, causing both of them, and that could be why those two things appear to be correlated. But nevertheless, it's a very interesting observation we have, and we have many different ongoing projects looking into what is causing the basal ice unit thickness variation and what is causing the variation of diffuse echo and the transition from diffuse echo into echo free zone. So for the next couple of slides, I'll go through some of the ongoing projects we see in NSF Codex. So a new study came out earlier this year by Ellen and Nicholas. They looked at that. They essentially went through the existing ice cores and examined the fabric structure within those cores and compared that to radar measurement. And their conclusion is that the incoherent scattering, which is essentially their name for diffuse echo, is most likely controlled by ice fabric transition, which actually agree with our observation here, the correlation between diffuse echo and basal roughness. And we have a UW PhD student, Emily, who's using different models to study the connection between basal roughness and the properties of basal ice unit and diffuse echo. And actually, Emily is doing a AGU presentation next week. So if you're going to AGU, please feel encouraged to check out her presentation. Yeah, like I mentioned, almost all the subglacial lakes we can identify from radar, they are all within the inner South Pole Basin on the inner side of the boundary. So there seems to be a hydrological correlation as well. And we don't know the exact mechanism yet, how subglacial hydrology correlate with basal ice unit thickness variation. There are different hypotheses floating around, waiting to be tested. There's this basal ice unit being melted away hypothesis, so on and so forth. I want to say this work of identifying lakes is done by one of our summer intern student, Hector, who is also giving a presentation next week at AGU. So if you have time, please come check out the poster and we can continue the discussion from there. complementary to this work, we're also trying to get an idea about the subglacial geological framework of this area. Now, this investigation is led by a PhD student at UT Austin, Megan Kerr. So I don't want to share too much about it, but there does appear to be a transition in the geological scheme across the boundary. Yeah, like I said, it's ongoing PhD work, so stay tuned for her paper to come out. And actually, Megan is now on her way to the field to join the ground geophysics team. They're hoping to get to the platter side to do ground radar survey, to do passive seismic and MT as well at platter side, if times allow, if they have good weather clearance, so on and so forth. All those different surveys together could provide a much better understanding of the subglacial geological condition, hydrological condition, and the connection between geology and the state of the ice sheet. And yeah, I was hoping to get a photo from the field team, but sending a photo to me is not their highest priority. So yeah. Another question we're trying to answer is whether or not the basal ice unit we're looking at here is a continuation of the basal ice unit at Gambursiv Mountain. Now, there has been multiple previous studies looking to what caused the basal ice unit at Gambursiv. Some hypotheses point to refrozen. So if we figure out, say we confirm it is actually a continuation from there, then we at least know how the basal ice unit was formed, right? But how do we answer this question? How do we test this hypothesis? The idea here is that if, say, two blocks of ice, they were formed by different formation processes, and you fly over those two blocks of ice by two different radar systems with two different frequencies, two different bandwidths, so on and so forth, and you compare the response, the cross-system difference might be different. So yeah, it's a little bit confusing logic. So different formation processes may cause variation, spatial variation, when you do cross-system comparison, which is great because our new codex survey is connected to some of the previous surveys in the region. So as you can see, the NSF codex radar set is actually connected to the AGAP Gambit survey done several years ago with two different frequencies. And one of our summer intern here actually looked into the thickness difference at the intersection points on those two different radar systems. What we found is that there appears to be a spatial variation in that cross-system comparison. So at the upstream part, codex survey, the UTIC radar system shows a much thinner basal ice unit at the majority of the intersection points. 35 out of 41 intersection points, codex survey shows a much thinner basal ice unit. The difference averages around 100 meters or so, some of them even over 200 meters. However, for the downstream part, the difference between those two different systems is not that significant. It's mostly half and half. 18 out of 33 intersection points, codex shows a thinner basal unit thickness, and the difference is, most of the difference is within 100 meters. So there is a spatial pattern here. However, I should say that this is a summer project for one of our intern students. We were not able to go through all the intersection points, so you can see there are a lot of other intersection points in this part we haven't examined yet. So it's still ongoing. We don't have a comprehensive review at this moment, but the preliminary result does show some very interesting spatial pattern. We have two students presenting on this work next week at AGU, Tim and Jocelyn. They both have a presentation on this project. So if you're interested, please feel encouraged to check out their presentation. The final piece of work, ongoing work I want to show here is that we're trying to investigate whether or not there is a rheology change in the basal ice unit here at the southern flank of Dome A. The motivation for that is because at Little Dome C, there appears to be a very drastic rheology change in that basal ice unit. Basically, the majority of the basal ice unit appears to be stagnant based on modeling study conducted at Little Dome C, and there are even some accreted ice on top of that stagnant ice. So the dynamics appear to be very complicated at Little Dome C, and obviously with huge implications for old ice exploration, right? But we do not know whether we can transfer that conclusion to where Codex has been working on, because those two areas are just so different. One is at a dome and one is at the flank of a dome. So there has been work going on at UW trying to evaluate whether to have the basal ice unit decoupled from the ice above it give us a better fit to the observed stratigraphy. It's still ongoing work, I would say, because there are just so many unknowns for this part. The rheology of the basal unit, of course, is important, but also the geothermal flux, the surface accumulation. We don't really know exactly what those values are, and they all could cause a huge impact as well. But with the potential field data we have, with upcoming ground survey data, we hope we can be more informed in terms of building the model and testing our hypotheses. And I do want to say that this new NSF Codex dataset offers a very unique chance to test this hypothesis over a much longer flow line, multiple 100-kilometer flow line here. So to sum up my presentation, we do see a pervasive basal ice unit across the Codex survey region. We see a relatively thinned out patch near the plateau site and a very rapid decrease in thickness across the quote-unquote mid-South Pole basin boundary. We don't see any correlation between the variation of basal ice unit thickness and topography, but there appears to be a very strong correlation between that and basal roughness and basal hydrology. And also the diffuse cycle appears to be correlated very well with subglacial roughness. And we see a very interesting spatial pattern in cross-platform comparison of the basal ice unit thickness. And there are many different ongoing projects trying to understand the formation and evolution process of the basal ice unit and whether or not, and if so, what is the geological and hydrological controls of such properties. That's all I want to share today. And with that, I am happy to take any questions.
Fantastic, thank you. Let me just remove. There we go. So if people want to raise their hand or indicate in the chat that they want to ask a question, feel free. Roger.
Yeah, thank you, Toby. Thank you, Shuai. Very much enjoyed that. That was great fun. My first question of two is extremely tongue-in-cheek and flippant, but seeing the flight lines out of McMurdo, I wonder if we put together a few $100s in cash and slip them to your Basler pilot, Do you think they'd go up the East Wind Glacier for us? Because we're in the middle of measuring seismic Q to see if we can correlate it with temperature, given it's on the edge of a volcano. But yeah, we'd probably better pursue that offline. Um, no, interesting. Your measure of roughness. I know it's not deeply serious compared to what you're doing, but that did you not think of doing sort of formal curvature or something like that?
I mean, when interpolating the roughness or
Yeah, it's
basically
just
increasing to.
yeah, there are lots of occasions when I'm having to deal with a measure of roughness along some profile, and yeah, the formal statistic of curvature, the y double prime over whatever the formula is with the set first and second derivatives seems to be
No,
um,
that's
the
definitely a good point. So I want to clarify that the map, this map here, and basically all the maps, I have been showing they are made for the purpose of releasing the data because this is an NSF funded project. We need to release the data within a certain time frame. So for this map here, I don't think there has been any sophisticated interpretation done. But that's definitely a good point because by looking to the statistics of the base roughness, there's just many different questions we can answer, right? So no, yeah, definitely that's a
yeah.
good point.
If you've got that curvature, you can always sort of think about stress focusing and so on, and comparing the radar power to how it would be scattered from curved surfaces and all the rest of it, and how representative it is, and so on. Yeah, that's smashing. Thanks very much. I've got another question forming, but I'll step back and leave it leave it to the others for a moment. Thank you.
Thank you. Thank you.
Great, thank you. Is there any other questions that people want to ask? Ed, you look like you want to. Go for it.
Okay. Yeah, Shuai, it's always been interesting why when you compare the AGAP and Coldex results, the Coldex survey sees layers to greater depth. And I know you've probably been thinking about this. Do you think it's because of improvements in the radar systems in the intervening time, or do you think it's the orientation of the flight lines somehow picking up fabric orientation differences?
Thanks, Ed. That's a wonderful question. I guess the answer is yes. Yes to all the possibilities. It is true that Codex dataset is about 10 plus years younger, newer than the AGAP data. There might have been some technology improvement, but also the major difference is frequency, right? Frequency and bandwidth, I think, are different for those
Mhm.
two systems. And yes, orientation wise, we do see a very, they're all very different. Um, I that's all. I don't know the exact answer, but in terms of orientation, I know that Jocelyn, who's a undergraduate researcher at UW, I think she's looking to the orientation independence of the visualized unit measurement as well as the appearance of the diffuse cycle, basically to examine whether you fly over the same spot with different orientation, whether the diffuse cycle appears differently or not. Yeah, that's all. Just to say, I don't know.
Are there any further questions? It sounds like a lot of answers are going to be given at AGU next week. Roger.
Thanks. Yeah, sorry, I'm happy to drop in another one. You were rightly saying that the radar attenuation is a function of temperature. Um, sorry if I missed it, but did you look at how warm it might have to be in that basal ice zone for the attenuation to be so high that you don't see the reflections from anything, any stratigraphic layering, because they are quite small reflection coefficients compared to the actual bed?
Yes, that's definitely, yes, that's a great question. So it's definitely one of the hypotheses we have been thinking about, is that the reason why we don't see any reflection in the basal ice unit or in the echo free zone is because the temperature is higher, the attenuation rate is higher, and even though there might be some weak reflection coming back, it's quickly attenuated away, and our radar sounder is just not able to pick up that signal. It's definitely one of the hypotheses we have in mind. I'm actually working on this project. It's kind of my pet project on the side. It's essentially to look into the attenuation profile vertically as it changes with depths. It is doable. It's just that basically considering the very bottom portion, the attenuation rate requires an understanding of the reflectivity of the rock. The approach I'm using, which is hard because we just don't know anything about the geometry here. So I'm making up a lot of assumptions that I don't know how trustworthy the result is. But we do see, back to your question, we do see a gradual decrease in the echo power here. The color here is the echo power of each horizon. We do see a decrease of echo power toward the point where our radar sounder is almost unable to pick it up. So it's definitely possible that the reason we have echo free zone is, temperature is higher, attenuation is higher. We can't see those weak reflections.
Yeah, and I'm just thinking and comparing it to the process that they call inverse Q deconvolution in seismic, where you get an idea of the Q values and you can then rebalance the strength of your reflections to compensate for it, and whether that would bring anything out deep down. But of course, if it's ultimately below the signal to noise of your system, then sure, you've lost it for good. I understand that. Yeah, interesting stuff. Thanks a lot.
Yeah, thanks. I mean, I don't know exactly what we can get from the ground radar system, but hopefully they can offer a different and separate perspective from their end in terms of attenuation rate and stratigraphy, so on and so forth. Yeah.
Are there any further questions for Shuai? Are you yourself going to AGU, Shuai, and presenting there?
Yes, yeah, I will be going to AGU, even though I'm not really presenting anything. I'm convening a session this year. Oh, by the way, I think I should give a shout out to my session here. So the session's name is called Strange Ice. It's essentially trying to bring together people from different disciplines and to talk about how we can work together to address some of the unsettled questions. And I believe the basal ice unit here is definitely a good example of that. We have different hypotheses, we have different groups working on essentially the same stuff. So, having a cross-disciplinary discussion together could be beneficial. So yeah, if you're at AGU next week and if you have time, please feel free to check out our Strange Ice session.
Okay, well, in that case, I think we ought to all thank you again for your presentation and for showing us your really beautiful data. And so good luck at AGU, and some of us will see you there.
Thank you.
Yes, and Russell, as Roger's just said, season's greetings to everyone, and happy Yuletide or whatever your favorite festival is for the winter.
All right, bye.